Hello YouTube, this is Harrison, and today we're going to talk about the stability of biological systems. There are two types of stability that these systems can exhibit: internal stability and external stability. Internal stability refers to a system that, when one of its state variables is perturbed, will return to its steady state values. External stability refers to a system that, when its input is changed a finite amount, will exhibit a finite change to the internal state of the system. We will be examining a two-species biochemical pathway and observe its stability through the calculation of the eigenvalues and by visual representation through a phase plot and time course plot. We will be using a script I developed in Python to determine the stability of a system. Variables a through d and g and h represent user inputs that will define the system's Jacobian matrix as well as the initial conditions of the two species. After importing relevant libraries and defining the span over which the two species would be modeled, Tellurium was used to model a two-equation linear system. From the user-developed Jacobian matrix, the eigenvalues were calculated and separated into their real and imaginary parts to be graphed in an Argand diagram. These values were also used to determine the behavior type of the system. And finally, both the time course plot and phase plot will be calculated and all shown in the command window to the right. Let's take a look at what that looks like. Upon running the script, we see that the first thing the program asks for is for the user to define the elements of the Jacobian matrix. We will be using predetermined numbers that will help me show each type of behavior that the system can have. Next, it asks for the initial conditions of the two species. For clarity, we will be sticking to 1 and -1. We see here that the script outputs that the eigenvalues are -1 and -2 with no imaginary components, shown in the Argand diagram. Most importantly, we see that the expected behavior is to be stable. This is represented in both the phase diagram, where both x values converge to 0, and the time course plot. Let's run the script again to see a different type of behavior. Again, we see that the eigenvalues do not have any imaginary parts. However, this time, one of the eigenvalues is positive in value. This results in the expected behavior of the system to be unstable, as perturbations will diverge to infinity. This is represented clearly in the phase diagram plot, where any x initial condition will diverge. This is also shown in the time course plot. Next, let's take a look at a system that will give us something with an imaginary component in the eigenvalues. Here, we see that the Argand diagram shows that both eigenvalues have imaginary components. While the system is stable, we see that this time the expected behavior is now to produce a stable spiral, which is best shown in the phase diagram. Running the script again, we'll see that spirals can exhibit both stable and unstable properties. While the eigenvalues look very similar in terms of their imaginary component, we see that this time any x initial value will diverge to infinity and lead to an unstable system. Finally, one last behavior that a system can show is called a saddle point. From the Argand diagram, we see that neither eigenvalue has an imaginary component. However, the phase diagram shows what's called a saddle point. This means that at single x values, the system will converge, but at any other x values, represented here and here, the system will diverge. And this all depends on the initial condition. Finally, let's take a look at what happens when the eigenvalues have no real components, but one is positive and one is negative. The result we see here is that it creates a center behavior. As shown in the phase diagram, the x values will oscillate and never reach stable or unstable conditions. While this isn't clear on the time course plot, or actually let's bump up the time to see what this time will look like. Let's change this to 10. Re-enter these numbers. As you can see from the time course plot, both x values will oscillate around 0. I think that's all we have time for today, but I hope you all learned something about the stability of biological systems. Peace out and have a great life. I love you.